Thank you very much for coming here today for our talk, Watching the Watchdog, Protecting Kerberos with Network Monitoring. My name is Tal Berry, and my colleague here is Michael Cherney. We both work for Microsoft. We work on the research team of the Microsoft Advanced Threat Analytics, a product that analyzes attackers' movement over the network. And how many of you have been here for the keynote? Please raise hands if you were here. So many of you, great. So I hope this presentation will be in the standard that the speaker, Harun, suggested for security talks, which means hopefully we will be able to give you something to work on to convince you that we are working on a tangible problem, a problem which is concrete and happens in real life. And we'll take a deeper look into the Kerberos protocol and a new breed of attacks against it, and also a new attack that we will expose, but also come with solutions of network monitoring. And we will also release a tool that you can try when you get back to your homes and your internal networks. So what are we going to talk about today? We'll start with discussing the attacker motivation. Why is this problem of attacks against Kerberos even matter? We'll talk about the details of the Kerberos authentication and Kerberos protocol. And we will talk about new attackers' paradigm of switching from stealing attacks to forgery attacks and what the attackers achieved by that. We'll talk a little bit about what it means to do network monitoring of the Kerberos protocol. And this is in the introduction. Then we'll take the really deep dive into 4 different attacks. And finally, we will wrap it up with some what we think actionable recommendations and a new tool that we are releasing. So let's start with the start. Why do attackers attack the Kerberos protocol? Because attackers need access. Attackers usually infect one machine within your network, but it's some random arbitrary machine. It's not where the data they want to get to resides, so they need to travel through your network until they reach their destination. And to do that, they need access. And access requires both authentication, which means verifying the user identity, and authorization. They need a user with just enough privileges to do what they need to access the data that they want. And since Kerberos is the default authentication and authorization protocol of the Windows networks, it means attacker must attack the Kerberos protocol in order to get the access they desperately need. So they have no choice. They have to attack or at least abuse the Kerberos protocol. Here is a quick review of the Kerberos protocol, of the authentication and authorization. So what happens on a Windows machine when you input your password? So let's say, and these graphics are by Benjamin Delpy, the author of Mimikatz. When the user inputs his password, let's say waza1234/, then the LSAS process within the computer derives keys from that password, encryption keys that are derived from this specific password. Then it sends an AS request, a request authentication service from the KDC. The KDC is the Kerberos server, and I will call it KDC or a DC for domain controller or Active Directory, but anytime I say it means the same, the Kerberos server. So the user sends something encrypted with the key that is derived from the password on stage 1 with AS request. The KDC tries to decrypt it with the user's key because the DC has all the keys. If they are successful, if the server is successful in decrypting it, it returns a TGT, ticket granting ticket to back to the user. And from there, from that point onwards, the user does not have to re-input their password. They use that ticket to request specific access to the servers, to the services they want. Say they want to access a file server, then they present the TGT in step 3. They send it again to the DC, and the DC looks at the TGT and derives a relevant TGS, a service ticket, which is specific to the resource the user wants to use. And we'll go into deeper details in the coming slides. Let's repeat again on the process, what happens in the Kerberos protocol when user input credentials. So the user inputs their credential right there, and a key is derived, and this key is used to lock a box, or in reality to encrypt a timestamp. That locked box is coming to the DC, to this triangle. The DC tries to open it with the key of the user, and if it's successful, then it puts in the same box, which means it encrypts with the same key the ticket, and this ticket, this TGT, comes back to the user. So there are very obvious attacks against this scheme, and it's stealing attacks. Attacker, which is based on the endpoint, can steal either the credentials, the key, or the ticket that comes in the end of it, and there are specific names: credential stealing, overpass the hash for key stealing, and ticket stealing is calling passing the ticket. So it's very obvious. You can steal any of these ingredients and disguise yourself as the user whose identity you had stolen. But stealing will only take the attackers so far, because you can steal, and attackers can steal only what is present. You cannot steal what isn't there. And therefore, they have to wait for the right user, the user with enough privileges, the user which is less monitored, and so on and so forth. And they have to wait. But waiting is boring, and time is money from the attacker's perspective. They don't want to wait with their operation until some administrator logs into the machine they control. And stealing things is, the tokens are unreliable in some sense, because they can expire. Kerberos ticket expires usually after 10 hours. Passwords and keys can change. So attackers don't want to start their campaign and in the middle understand that their password and access is no longer valid and go back to square one. And for some scenarios, basically there is no Mr. Right. There isn't a right user. That just does not exist. For example, if an attacker wants a user with administrative privileges, so they can access everything, but yet this user won't be listed as an administrator, so it wouldn't be monitored by some monitoring tools, then there isn't such. So you cannot steal it. But if attackers use forgery, and they are forging the relevant Kerberos tokens, and they are fiddling with the protocol, they can get an on-demand privilege and access as they want. So they move on, attackers, from stealing to forgery. And we will talk about 4 specific attacks: the forged key, the skeleton key, forged ticket, the golden ticket, and 2 variants of forged pack, and we will explain what is pack, MS-1468, and the new attack we developed, the diamond pack attack. And just before we go on to the specifics of this attack, we said that everything can be protected and detected using network monitoring. So what do we mean by that? We mean that all of these devices, every device that wants to access resource within the network must pick Kerberos with the Active Directory. So regardless of the operating system, this could be an iOS, Windows, or Linux. And these protocol messages are flowing to the Active Directory. A security device that passively monitors that traffic, just port mirroring on the switch in front of the Active Directory, the Kerberos server, we will show that it is enough to mitigate and detect all of these attacks, and very importantly, without knowing any of the Active Directory secrets. This device does not need to know any of the passwords within the domain. With that, let's start with the first attack, the skeleton key. Michael, it's yours.
Thank you, Tal. So let's talk about skeleton key. What is skeleton key? Skeleton key is actually a really cool malware. Attackers installing a malware on DC to be able to authenticate as any user by using one unique secret password. The result is amazing. Attacker can now log on to any workstation or any server, either via terminal or over the network, using that single secret password. But the original user experience is not hampered. It still looks and feels the same. So let's just experience that and see how this looks like. Let's say we have an administrator whose password is admin123, and the secret password an attacker has configured to be password. So now administrator approaches his administrative station, enters his password, logs in just like it should, and then by mistake he enters the wrong password. And again, just as he should, he or she, there is a failure. But now when an attacker enters his secret password, boom, he also succeeds to log in. So after the skeleton key malware work was published by Dell SecureWorks, Benjamin Delpy also added support to Mimikatz for the skeleton key, and now it's productized for all. Everybody can try it. Now let's see how the skeleton key works. First, let's focus on the fact that Kerberos supports multiple encryption types. From this fact, we can conclude that the client and the server, the domain controller, need to negotiate to know which of the encryptions to use. How this negotiation happens. User at the client machine enters his username and password, and the client machine sends to the domain controller what the supported encrypted types from his perspective. The domain controller takes this and cuts it with what it can and what are the keys, type of keys this user have in an Active Directory database. So in this case, it has RC4 and AES keys. So it will respond, okay, I can talk with you RC4 or AES. The client hopefully will choose the more secure one, calculate the hashes from the user password accordingly, encrypt the timestamp and send it to the domain controller. The domain controller will try to decrypt it with according key type of that user, and if the decryption is successful, it will send back the ticket granting ticket, the TGT. Now, this is how it looks over the wire from the Wireshark perspective. Client sends all the encryption types it supports. The domain controller answers with what it can do, AES and RC4, and the client responds with a timestamp encrypted with AES. Now, what is different between AES and RC4 and how it's related to this malware? We said that client sends the timestamp encrypted with a derivative of the user's password. So if an attacker would sniff that timestamp, attacker could attempt a brute force attack. To make those brute force attacks more difficult, there's two known techniques. One is salting. Its goal that for two different users, even if their password is the same, the key, the hash, would be different. It's done by appending a salt string to the password while deriving the hash. AES is using the username as a salt, making it unique for each user. RC4, on the other hand, doesn't use any salting. Another technique is key stretching. Its goal is to increase the amount of CPU required to check whether a single password is correct one or not. Therefore, drawing the mass brute force attack infeasible. AES is using PBKDF2 standard, which is a password-based key derivation function 2 standard, which is basically performing thousands of SHA rounds. In case of Windows, it's 4K rounds by default. RC4, again, doesn't do any key stretching. How it's relevant to our attack? To the attackers and skeleton key? Attackers, in this case, love RC4. Why? Because due to salting, identical password would create different AES key for different users. And therefore, that one unique password, which secret password which attackers configured, we would have to either calculate it for each user authentication in real time, which would require a lot of CPU, or pre-calculate it and store in memory, which require a lot of memory. What attackers do in this case, we just cause domain controller to downgrade to RC4. And how they do it, I said that the malware is cool. What it does, it actually patches in memory the code of the domain controller. One function, which is it patches, is a function which checks whether the user have what it's called Kerberos new keys, which is basically AES keys, and return false, therefore drawing those keys practically non-existent. And another one is decrypt function. Decrypt function is that same function which tries to decrypt the timestamp and therefore check whether the user is what he claims he is. It's patched in a way so that the original decrypt, it first calls the original decrypt function, and if it fails, it calls it again with a hash of the secret password. So if the user entered the password correct, it will work as expected, user will be authenticated. If the secret password will be entered, again, it will be authenticated. If it's neither of them, therefore wrong password, it will fail. So this is how it looks like. The user enters, the domain controller is infected with a skeleton malware. This means that practically or effectively, each user now have two RC4 keys. One, the original one, which is derivative of his own password, and another one is the derivative of the skeleton key configured password. And another effect is that AES keys are now not accessible. They practically do not exist. So now when the user enters the skeleton password, client is not affected. This is a very important notion here. Client is not affected by this malware. This malware only exists on the domain controller. But the domain controller now looks and says, I only have an RC4 key for this user. So the only one I support now is the RC4. And the client will calculate the RC4 hash, encrypt the timestamp with RC4. The domain controller will check that the encryption is correct, either with original password or again with the skeleton key, and return the DGT back to the client and to the user. So this is how it works. This is how it looks over the wire. This is before the domain controller was infected with the skeleton key. Client sends all the encryption types. Domain controller responds with all of them. And the client sends the timestamp encrypted with AES. After it was infected, client, as we said, is not affected. So it sends just the same, all the encrypted types, all the encryption types it supports. But now the domain controller responds only with RC4. And therefore, client will also encrypt the timestamp with RC4 and send it back to the domain controller. So how can we detect it? We said that the essence of the skeleton key malware is to downgrade to RC4. So therefore, we can detect it, this behavior, because it also manifests itself over the network. We can know that the user should be offered AES by DC. How? Because either we saw in the past and learned that DC domain controller was offering AES to the user in a previous access, or by judging the domain function level and the user capabilities. So if you should be or was AS before, why it's only RC4 now? The Microsoft Advanced Threat Analytics monitors the domain controller and detects the downgrade activity. This is the screenshot of the alert and alerts on it, saying it's probably the skeleton key. Tal also wrote the script which can actively check where the domain controller is infected. There's the link here to download this script and try it. And this screenshot is the screenshot of the Mimikatz, which infects the domain controller with a skeleton key, and the script, Tal script, which runs and detects that it's indeed infected. Now we'll return to the Tal to talk about golden ticket.
Thank you, Michael. Let's move on to the next attack and remind ourselves again what is Kerberos. And we said the Kerberos is the default authentication and authorization protocol, but we only talked about authentication, which means verifying the identity of the user. We didn't speak about authorization at all, which means how this system assigns privileges to the user. So let's do that. And in Windows networks, authorization is realized and implemented with a PAC, Privilege Attribute Certificate, which holds all the authorization data you can see here, which means basically all the groups you are a member with. So this user, the administrator, is member of domain admins, enterprise admins, schema admins, and so on and so forth. And if you can think the brick and mortar analogy for authentication authorization is ID card. So your picture and name is the authentication part, and authorization is the part that says what you are allowed to do with this card, maybe to drive some vehicle or enter some place. So this is authentication and authorization, and the PAC is not only does not only contains groups, but also has some security measures within it of signatures, and we'll talk about that. So how is the PAC enters the game of Kerberos? So when the user authenticates to the DC, and assuming that the key was indeed the right one, the DC calculates this PAC, which again, this is all the groups that the user is member in, and sends it along the TGT, embedded within. Then when the user requests access to a specific resource, that PAC is being copied from the TGT into the service ticket. And that's the way that authorization is implemented in Windows with Kerberos protocol. A quick word and reminder of what is digital signature, specifically HMAC. So this is the Wikipedia definition: message authentication code, MAC, a short piece of information used to authenticate a message, and HMAC is just a hashed MAC, a MAC that uses a hash. And we can see in this diagram, again from Wikipedia, that the algorithm, the hashed MAC algorithm, takes a key and does some calculation with the message and the key. And the receiver, which also has the key, can verify that indeed this message has not been tampered with, because the signatures remain the same. So this is the basics of digital signature. And so what promises that the TGT is indeed untouched and its integrity is not has no problems? So ticket integrity is guaranteed by the fact that the ticket itself is encrypted, and it's encrypted with the KERB-TGT key. KERB-TGT is the internal Kerberos account. And therefore, since this is encrypted, attacker cannot simply edit the TGT because they don't know the KERB-TGT. And on top of that, the PAC integrity itself, even though that is embedded within within the TGT or service ticket itself, and as a result, it's encrypted too. It's also being signed twice by the Kerb TGT. As you can see in the bottom of the pack illustration, there are two signatures of the server on it, again using the Kerb TGT key. As we can see, the Kerb TGT key here is a single point of failure. Everything depends on it. So if the attackers are able to obtain the Kerb TGT key, then they can create the famous or the notorious golden ticket attack, which means if they steal the Kerb TGT key from Active Directory, they can create arbitrary tickets. And again, this was implemented in Mimikatz, in Benjamin Delpy Mimikatz. And I like this quote: "A golden ticket is a homemade ticket. It's done with a lot of love and the Kerb TGT key." So what happens here? And this is the attackers, how attackers' request for a specific service looks like with the golden ticket. The attacker gives its exploit, say Mimikatz, the Kerb TGT key and the ticket details, the groups that the attacker wants their user to be member in. That exploit kit bakes a TGT and injects it, either injects it to Elsass or has its own implementation of Kerberos. And from that TGT, the attacker is able to request access to specific resources as in before. So let's play a little game. Let's play Spot the Difference. So this is how regular authentication authorization look like. The 5 steps that we had seen earlier. And this is how malware using golden ticket authentication looks like. Can you spot the differences? Well, yeah, exactly. There is a missing step there. Again, this is not by mistake. This is the essence of the attack. The attacker tried to skip the first authentication step and start from the middle already with a TGT that they baked in advance using the Kerb TGT key. And how does it look over the network? So this is again a normal authentication. You can see here in the AS reply, which is the second step of the 5 steps, you can see here in the red box, this is the ticket that goes back to the user. I'm not sure you can see it, but it's a blob. It's a long buffer, long encrypted buffer, and it's encrypted. Network monitoring cannot see the contents of it, but we don't need to, because what is important is that the user quotes this buffer verbatim, byte for byte, in the TGS request, as you can see here. And if you don't see, you can believe me that the encrypted part, that ENC part in this screenshot is the same between the AS reply and the TGS request. And in the screenshot at the bottom, you can see a typical session of Kerberos, which contains, again, a single AS reply with a ticket in the ENC part, and then a series of TGS requests asking access to various resources, all has the same encrypted ticket information, encrypted TGT information in them. So the network-based detection is trivial. From that, the security device tries to recouple the TGT and TGS request with its parent in the AS reply. And if this security device is unable to find the TGS request parent, the AS reply that created it, it alerts on possible golden ticket attack. And this is just to show you that this is not only theoretical issue. You can see here, this is a slide from CrowdStrike, from RSA this year. And this is a threat actor, I think Hurricane Panda, they named it. And this threat actor, one of the steps in establishing access to the network was create a golden ticket. So this is a very valid attack, and it is used in the wild. Let's move on to another attack, another forgery attack that, again, was found in the wild, MS-1468. I like this tweet by Gavin Millard giving a real-world analogy to this attack. It says, MS-1468 is like buying a regular ticket to an air flight, writing, I'm the pilot on the ticket, and then the steward says, welcome, Captain. How would you like your coffee? So you start as a regular passenger and end up within the cockpit as the captain. And again, this is not a theoretical attack. This is the way that the Kaspersky attackers were able to breach Kaspersky internal network. So this is indeed something that advanced attackers actually do. And let's talk about the technical details of this attack. So this is the pack that we remember from the golden ticket attack. And it's embedded within the encrypted ticket. Let's talk about what happens when the user sends the TGT and requests a TGS. What happens to the pack? So what happens to the pack? The KDC first verifies the signatures. And if the signature is found to be valid, which means the pack was not tampered with, it just copies the pack from the TGT into the service ticket and resigns it once with the server key, so the server will be able to validate that indeed this is a valid pack, and signs again with its Kerberos TGT, Kerb TGT key. So if the server for some reason wants to do extra validation, it can send this pack back to DC and ask it if indeed this is properly signed. And here is the essence of the attack, the vulnerability. The vulnerability was that keyless signatures were allowed. So in theory, in the specification, only HMAC, which means a hash with a key, should be used to sign. But the vulnerability was that erroneously, the KDC accepts keyless hashes as signatures. For example, you can sign this pack with MD5, which means that anyone can sign, because there is no key, no secret element in this process. Therefore, there is no point in this signature. Anyone can sign it. But is it really that serious? Because we said that the ticket itself is encrypted. So attackers cannot just overwrite the pack in a valid Kerberos ticket with the pack they signed on with MD5, because it wouldn't work. It wouldn't be decrypted properly. And if they can encrypt it, and they already have the Kerb TGT key, so why bother with it? They can just do whatever. Okay, but there is a way to exploit it without knowing the Kerb TGT key. So here is how it works for the attackers. The attacker first requests an AS request, authentication request, but they ask for a packless TGT. Please give me a TGT without a pack. This field include pack equals false. Then the attacker requests with a TGS request a service ticket with a fake pack. So they quote that packless TGT, but they have a new field there called authorization data, which is optional. And in that field, they fill in their MD5 signed pack. So this is an interim summary of what's going on for the attacker. The attacker still needs a password. So a regular AES request is performed, but the attacker requested to be without a PAC. Then the attacker uses that ENC authorization data. Thank you. The attacker uses that ENC authorization data field in order to put in the PAC that they signed with MD5 and send it to the DC. The DC just embeds that PAC into the service ticket that is used to access the specific resource that the attacker wants. But it does not really work because servers, the DC before the patch was able and they accepted PACs that are signed with MD5. But servers were already patched and they do not accept PAC that is signed with MD5, and therefore they would reject that ticket because it's not properly signed. But the attackers do not quit, and they introduce another stage in their attack that fixes that situation. So in that attack, instead of directly requesting access to the resource that they want, they have another round. In stage 3 and 4, they send the TGS request. They want specific access to the Kerberos internal service, the KERB-TGT. And usually it is used to renew a ticket. If you have a ticket that is about to expire, you create a TGS request to KERB-TGT and you get a new one. So that's what they do. They request request access to KERB-TGT. The KDC just embeds the PAC they specify in the ENC authorization data into the service ticket in stage 4. And then in stage 5, they request an access to the resource they actually want to access to. By then, they have a TGT with a fake PAC within it. But what happens on the server, we can see in the next slide, the KDC follows its usual flow. First, it verifies the signature. The signature is MD5, but since the KDC is vulnerable and is willing to accept a PAC signed with MD5, it said that's okay, and copies the PAC information, the privileges, and then it re-signs, but this time properly. It signs it with MD5, with HMAC SHA-1 and HMAC MD5 with its key, with KERB-TGT key and server key. Okay, and using this stage, attackers are able to get a valid, a kosher ticket. Oh, sorry. So this is how a regular passenger, a regular domain user, now becomes the domain admin, if they like to, and can breach the Kaspersky internal network. So let's discuss network-based detection. So for unpatched server, the way to detect is detect an AES request with PAC request equals false, because the attacker wants a ticket without a PAC, so they can bring their own PAC into the game. Then see an ENC authorization data field, which is not null, which contains some authorization data that is used by the attackers to put their PAC in. And finally, verify that the target server indeed needs a PAC, which it's another field in the Active Directory. So even though that some of these fields can normally have this value, but having all three of them together doesn't make sense, and we can alert on that and detect this attack. For patch servers, it's even easier to detect this attack And the point of detecting attack against patch servers, even if it wouldn't work, because you want to know that you were under attack, even if it wasn't successful, is that the KDC will return an error which is very indicative to the situation that the signature type is not supported because it's patched and it's no longer willing to accept MD5 as a signature. Sorry, I have to stop doing that. And this is how it looks, a network-based detection of MS14 of a fake pack, exactly based on the criteria we had mentioned before. And now we move on for the last attack, forge pack, the diamond pack. Here you go, Michael.
Thank you, Tom. So let's talk about diamond pack. This is diamond pack is a novel attack variant, which is an offspring of two attacks. It takes the idea of stealing the KRGT from the golden ticket, and then takes an attack flow to embed that the pack from the fake pack. And the result is a diamond pack. So how the attacks go for the attacker? The attacker would obtain KRGT, and then it will create the rogue pack with whatever privileges an attacker needs, but it will sign it not like in a fake pack attack with MD5, it will sign it just like the Kerberos domain controller would with the KRGT key. And it will use the fake pack attack flow to embed, to push this rogue pack to the TGT and then to the TGS. The exploit from the stage looks very similar, the same practically as a fake pack, with one major difference. Attacker first bakes the pack, signs it with KRGT, which is signed with a diamond, this is a diamond pack. Then it goes and doing an authentication request to the Active Directory and say, give me the TGT without a pack, no pack op. Receives back the TGT without the pack. It goes again to the Kerberos domain controller, to the Active Directory, and asks again for the TGT, it's KRGT service. This time, inside of end authorization data, there is a diamond pack. Pack signed by KRGT. The domain controller returns TGT with copied pack, and then the attacker now will go and ask to the access to a specific resource, basically asking, doing a TGS request. This pack will be copied over to the ticket, to the service ticket. But since the pack is signed correctly with the KRGT, the domain controller will accept it and it will pass verification. Will resign it with KRGT and with service password, and return the ticket, the service ticket. This means that even if the server, even if Active Directory is patched against a fake pack, the MS1468, this diamond pack will still work. So the obvious question is why to use the son, the diamond pack, instead of the parents, but we just explained it, because the golden ticket is easily detectable over the network, because, and not only over the network, because there's a coupling of authentication response, the authentication request response, and TGS request. Fake pack is patched, it's no longer live. So we have a diamond pack attack, which gives us an unbound privileges, just like a golden ticket, but with legitimate family tree, legitimate flow over the network. But fortunately, since the flow is just like the fake pack flow, the same logic which detects the fake pack will detect the diamond pack, yes, sorry. And again, the same alert will be in advanced threat analytics. So here we finish and we will conclude. The first conclusion is that attackers no longer stop at stealing existing identities, just not enough. We are working to subvert, we must subvert the inner working of the Kerberos system to be able to forge identities and privileges, which previously didn't exist. But network monitoring, we can protect against both of those paradigms. So let's put a network monitoring leash on that Kerberos dog. And you can download the scanner against the skeleton key from the link on this slide. You can also evaluate the advanced threat analytics if you like. And thank you very much. Any questions? Which one? This one?
The presentation will be on Black Hat site, so you can, just click it from there if you like. Any other questions? Okay, so the question was, is this monitoring approach only good against the attacks we had shown here, or is it something more generic? So the short answer, yes, it's a general solution, a generic solution. You can detect all kinds of other attacks. For example, stealing attacks. It's easy to detect with network monitoring. For example, pass the ticket. You see that a ticket was assigned to a certain computer, and all of a sudden you see it from another computer. So from the network perspective, it's very easily to see this anomaly, but if you don't have network monitoring, how can you spot it? Everything works out perfectly. So this is a very generic approach to detecting this kind of attack, and not only the one that we had shown you. Thank you. Yes, please. So the question was, what is our recommendation if you were already infected, attacker was able to obtain the KERB-TGT key, and what do you do now? So obviously you need to change that KERB-TGT key, and look for it at TechNet, Microsoft TechNet. There's a way how to change it. In fact, you have to change it twice, because one generation older KERB-TGT key is still valid. And in fact, there is also, if you want to go the extra mile, there is a script you can download from TechNet that periodically rotates your KERB-TGT keys. So even if you are not aware that someone stole your golden ticket, because typically what it used to be is that administrator never changed KERB-TGT key. In fact, they weren't even very aware that it existed. So attacker stole it once and got access to the network forever. But now there is the script that rotates that KERB-TGT key. So even if your domain controller had been exposed and attacker obtained KERB-TGT, so it's only good for a few days and not forever as it used to be. Yes, please.
Have you ever considered replacing the old Kerberos protocol with something totally new?
So the question was, if the Kerberos protocol is so vulnerable, why don't we start with something else, something new? The short answer is impossible, very much, because let's take, for example, the NTLM protocol, the older authentication protocol that Microsoft had used and tried to, and in fact, from Windows 2000, so 15 years ago, Microsoft default authentication protocol was Kerberos and not NTLM, but still, even Windows 10 still supports NTLM because of backward compatibility and all their application and so on and so forth, because this is a protocol. It's not something on your computer. It's on computer, it's on the DC, it's on the application you access. So it's very hard to change that protocol. And even though Microsoft is trying for 15 years to get rid of NTLM and it's able to limit its use from version to version, it still cannot get rid of it altogether. So even if we changed Kerberos, which is a good protocol but has some attacks on it, it will take us at least 15 years to get rid of all of the ecosphere of it. So it wouldn't. So I think the best strategy would be to have monitoring on it and strengthen it and not replace it with something else. Okay. Okay, if there aren't further questions, thank you for coming today. You can find out, there is some Twitter handles for us, and you can reach us and ask anything you want, and we'll be here after the talk. So thank you very much.
Thank you.